So last time I said that the benzaldehyde could be oxidized in air. Here's a bottle of benzaldehyde. This isn't the same bottle we used for the cannulation for the experiment, but it's a very pure bottle of benzaldehyde, and it didn't look like it had any solid in it. It looked all liquid. So I said that the benzaldehyde can be oxidized from its sweet cherry smelling liquid to a solid benzoic acid and by oxygen in the air. But when I tried to do the experiment in the fume hood with a little bit of benzaldehyde, I didn't really see any solid form. I think it's because it evaporated before it could be oxidized. So I tried to repeat the experiment. I took a sand bath without any sand, basically a bowl. I weighed it empty, and then I added benzaldehyde to it. And it's hard to see right here, but if I take this picture and blow it up, there is benzaldehyde there. Do you see it? There's this benzaldehyde liquid. It's right there. That's the benzaldehyde I added. So added it to that, and then I just left it on the counter to oxidize in the air. And I came back in a couple days to check on it. So here's the mass of the sand bath without sand, but with liquid benzaldehyde. And if you subtract the empty mass of the sand bath, this has no liquid benzaldehyde. I start with 1.63 grams of liquid benzaldehyde, and let's see how it turned out. It does not look like I was lying. Got lots of crystals. Nice, pretty, huh? And when I give it a sniff, this doesn't have any smell of cherries to it, so I think all of the liquid benzaldehyde has been converted to the solid benzoic acid, which doesn't have a cherry smell. So my nosometer says the reaction is complete. Now I'll get an IR of the suspected benzoic acid. So I've got my ATR adapter with its zinc selenide crystal, nice and clean. I'm going to start off with the background scan. Let's go back over here. Instrument, scan background. I just turned on the computer, and so it's warming up. We've got ourselves here an HP compact from the probably from the late 90s, maybe. Let's see, but it works as long as you keep it off the internet. It just keeps going. There we go. Yeah. All right, so here we are, 1 of 4. The background looks good. That's what we usually see, right? Boom. Okay, we'll overwrite the old background, put on this new background. I like it. Looks normal to me. I'm going to delete it. Now I'm going to add some sample of the suspected benzoic acid. So pause the video and write this number into your, well actually no, this isn't going on the report worksheet. You could keep track of it if you want for the fun of it. I'm crushing down that solid onto there. I'm going to take scans over here. Instrument, scan, sample. Okay, see how it goes. Benzoic acid, of course, should have the carbonyl OH, not the carbonyl, the acids OH here, this big mess around 3,000 to lower range. And it should also have a strong carbonyl signal, 1700. And just over 3,000, we might be able to see the sp2 carbon dihydrogen signal. All right, let's see how it looks. Yep, that looks like benzaldehyde to me. Let me label some peaks here. Bring up the vertical cursor. Pull it over. I bet this is the, yeah, just over 3,000. That's an sp2 carbon dihydrogen. All this is due to the OH of the acid, the carboxylic acid. I'll just kind of pick out a couple of them. There we go. And then this here is the carbonyl. Yes. And I'll add a text box. Take a picture of this. Let's look at this benzoic acid IR a little closer, make sure it is benzoic acid. So here's benzoic acid, and if we look closely, you'll see, yeah, that's a good carbonyl signal there. For the acid, it's at 1672.39. wave numbers, reciprocal centimeters, so that's right in about 1700 where it should be. And then our OH of our acid, it shows up all this mess right here. And yep, this is all within range. And finally, the sp2 carbon to hydrogen bond, representative of all 5 there. It's showing up just over 3,000 like it should at 3,068.57 reciprocal centimeters. So this looks good. It's definitely got the characteristic signals we should have. And let's look and compare it to literature spectra. So here's our spectrum again. And here it is from the SDBS website. And oh, they don't look exactly the same. Look at the intensity here and here. Oh yeah, this is actually benzoic acid as a Nujal mole. And remember, a Nujal mole is when the solid benzoic acid is dissolved in a hydrocarbon solvent Nujal. And then so we have all of the hydrocarbon solvent signals as well as the benzoic acid signals. So we don't want to compare this one to ours. If we have what we do want here, the KBR disk, that'll be most like ours. So let me click on that, and here it is, KBR disk, and yeah, they match up really well. Look at that, right around here, the carboxylic acid OH, the carbonyl, these 2 here, these 2 here, and then we got a single little guy, and then those 2. Fingerprint region looks really good, Nick. And we got, I'm in my living room recording this. Oh well, crazy times. Okay, so yeah, looks really good. Okay, let's bring this little side experiment to an end. Finally, we'll look at the yield of this reaction. So we started off with 1.36 grams of the liquid benzaldehyde, and let's see how much benzoic acid we should make. Theoretically 100% yield would be. So benzaldehyde's got a molar mass of 106 grams, 106.12 grams benzaldehyde per 1 mole, so that'll convert my grams of benzaldehyde to moles, and then 1 mole of benzaldehyde makes 1 mole of benzoic acid. I'm not sure of the stoichiometry of oxygen in this. I guess it's half an O2 gets introduced, yeah. So, but we don't need that. There's excess oxygen in the air around us. So we have 1 mole of benzoic acid, weighs 122.12 grams. That makes sense, right? Because it's heavier atom by 1 oxygen, so this is just 16 more. So our mass of benzoic acid produced should be more than the benzaldehyde we started with because we're adding an oxygen to the molecule. And yep, we're expecting 1.88 grams of benzoic acid. How much did we get? Well, those nice pretty crystals of benzoic acid in the bowl I showed earlier, they had this mass. The bowl, the sand bath without sand, had this mass. So we produced 0.39 grams of solid benzoic acid. So not quite as much as we were expecting, huh? So what's the percent yield? So we actually got 0.39 grams of benzoic acid made, and theoretically we could have made 1.88 grams max. So it was only a 21% yield of the benzoic acid. So why do you think that is? Why was the yield so low? I have the reason I believe it is. It's related to the first time that I tried to do this, where I just put a little bit on the fume hood counter, and then I didn't really see any solid later. Well, I think it's because the benzaldehyde liquid is evaporating before it can be oxidized and remain a solid in the container. So 21% yield makes sense to me. Okay, now back to our experiment of making benzoin. Hope you enjoyed our little side trip here. Here's our reaction flask after a few days, I think it was. I left it in the dark. It looks like we got a lot of benzoin crystals that formed. Looks good. And we'll confirm that those are benzoin crystals with spectroscopy later. So let's zoom in and look at this a little better. Yeah, it looks like nice little like lily pad looking crystals. And it's crystallized all the way down, not just on the surface on the top there. So what do we have in this solution? It's mostly ethanol. That's the solvent we added the most of. And then water. And then, of course, sodium hydroxide we added. And any benzaldehyde that might not have reacted. And the thiamine catalyst deprotonated, probably also protonated in there. So these molecules are all dissolved in the solvents. And then we also have benzoin. That's what we want to isolate. How can we isolate it? Well, it's crystals. it's the crystals, so we can filter off this solid from this stuff that's dissolved in these solvents. So we're going to set up a vacuum filtration, and we have a water aspirator here with a splash guard, and it's going to draw vacuum into it. How does that work? Well, as water travels down the aspirator, the splash guard just prevents it from splashing up on the counters too much. As water flows down quickly, it sucks air into this tube. It draws air this way to cause a vacuum for us. So this vacuum gets drawn through the Buchner funnel here, through its filter paper, and then into the filter flask, which is drawing the air out of it this way into our water trap bottle. So this water trap bottle is put under vacuum because it's being drawn, the air is being drawn out this way to the water aspirator. This other clamp here, this is clamped off this third tube. That's just like a release valve. We'll look more into detail with the video shortly. Hooked up to the side arm of the aspirator, the water aspirator, and I have the water splash guard on the bottom, and then this vacuum hose hooks into our water trap bottle, which has a release valve here that's closed off, and then another hose that leads out of the bottle to the filter flask. And this is meant for if water does come back up through the water aspirator, it has to fill all the way up here before it can start to get into our filter flask where we don't want it. So let's check and see if we've got good suction. I'll turn on the water and I'll put my hand on this area to see if it's got suction there. So put the water on full blast, and that splash guard's working well. It's not splashing up on the counter. Put my hand here and let's see. Oh, yep, I feel suction. You can hear it. Yep, there's suction there. Let's do it with, let's have some fun with some parafilm. Put some parafilm over the top of the filter flask, and now I'll turn on the water aspirator video in slow-mo and see what happens. Here's a view looking down the top of our Buchner funnel, and you'll see it's got the little holes in it for the solvent to go through, but our crystals might actually get through those holes too, even though they're pretty small. So we're going to put filter paper over this. So I didn't have the exact size filter paper, so I just took a bigger piece of filter paper, traced an outline in pencil, which is better than pen because a lot of the organic solvents we use will dissolve pen ink but not pencil. And then I cut it out. Put it inside of the filter flask, Buchner funnel, and set it up for vacuum filtration. And after I did that, as I was doing that, actually, I cooled down the solution of crystals in an ice water bath. Notice I use a beaker that's a little bit bigger than the Erlenmeyer, so there's no way this ice could all melt and then the Erlenmeyer fall over. And here's a nice picture with the cork off, looking down in our pretty crystals about to collect. So I'm being good. I cleaned out my filter flask. It's wet with water, which is fine because I'm going to be using ice cold water I prepared here to wash my crystals. I just put some ice in the bottle and I filled it with DI water. I don't know if that matters. I'm not sure if our ice is made with DI water or not, or tap water. I think either is fine. And I have my Benzoin crystals cooling in an ice water bath for about the last 8 minutes. And I'm going to break those up with a spatula, and I'm going to put them in my filter flask, which it might look dirty because it's kind of hazy, but what it is this filter flask is a fancy one. It has a protective coating, if you could read that, protective coating. And you can see, I'm going to show you a picture of it, and you can see right here where its protective coating ends. And so this protecting coating can get like a haze to it, especially when it's exposed to acetone during washing. So it's actually clean on the inside. And I've got my filter paper that I cut out up here, and it's a little bit bigger than the circle, but I just pushed it down. And I'm going to make sure that filter paper sucks down well by wetting it first with some ice cold water, and then quickly swirling my broken up crystals here, pouring it in and then rinsing it with the ice cold water to see if I can wash off the crystals. I should be losing most all of this yellow color And if it's the same as always in the past, it's gonna stink kind of like cat urine. But also, if you just get barely a hint of it, it smells like cooked chicken, like roasted chicken. So a little bit might smell okay to you, but a lot does not smell good. We'll see. All right, here we go. We're gonna filter. I'm gonna turn on the water aspirator and get it started. I'm adding ice cold water. I want to see this filter paper suck down so that the liquid can get through the filter paper but not around the outside of the filter paper. And then I'm going to take my crystals, swirl them around good, give them a swirl and a quick dump in the middle. It's looking pretty good. That's a good yield. And yes, if I smell it from about here, it does smell kind of like chicken. I rinse it out, ice cold water. I'm gonna look at this and I'm gonna determine, is it dissolving the product too much? Should I not pour it on hastily? It looks okay, actually. It's looking good. I've had this under vacuum for about 5 minutes. Now I'm gonna turn off that vacuum and transfer the crystals to my pre-weighed watch glass here. So before I turn off the vacuum, I'm gonna break the seal. All right, this way when I turn off the water aspirator, it does not allow a backflow of water. Okay, so I can take this apart. You can see in here, we did get some crystals to come through, but not too much. It's acceptable by me. So now I'm going to take my filter paper, carefully take that out and try to get all these crystals onto my watch glass to dry. I'll get some tweezers. I'm going to gently scrape off some of the crystals. I'm not going to expect 100% yield, and that's okay. I don't want to scrape the filter paper fibers off, but I am going to crystallize this. So if I have a few filter paper fibers come off, it's not the end of the world. I think I'll be able to take care of those during my crystallization. Okay, so now I've got pretty much all my crystals on here, and I'll break them up a bit to give them more surface area to evaporate away the water and ethanol. And then after I've given this time to dry, I will weigh it to get a crude yield, and then I'll crystallize it from ethanol and get a final yield of that. But I'm gonna let this dry overnight or longer. We'll see when I get back to lab. You don't have to let it dry that long. You can go right onto the crystallization right away if you like, if you're doing this in lab. But I'm going to be doing some other things, so I might as well just let this dry. Here's a watch glass that I collected the crude benzoin on. It weighed 143.22 grams. And then here's the crude benzoin on the same watch glass, and it's a 147.84 grams. So this benzoin, this crude benzoin, it's got some impurities, but it also could be significantly wet by your crystallization or by the reaction solvent and wash solvents. So this could be wet. So I'm gonna calculate this out, but I'm gonna let this sit and dry over a couple days and then reweigh it and see if it gets lighter. So it's 4.62 grams of the possibly wet crude benzoin, and we'll check back next video and see how this changes, if it does. So I'll see you in the next video. You can write this number down, but you don't necessarily have to put this in your reaction table just yet.